So yeah, hello, I'm Professor Michael Nowak. I work in the Department of Physics here at Washington University. I've been here for about 4.5 years now. I came here from Boston, having worked for a NASA satellite that I'll show you a little bit from at MIT for the past 20 years. I've been doing astrophysics of one sort or another for about the past 30 years, specializing in black holes and neutron stars, and that's going to be a lot of the discussion that we have here today. So this is the final talk in the series celebrating the 100th anniversary of the discovery of the Compton Effect. And our previous talks were a bit more historical, and I will have a little bit of historical stuff here, but I'm going to tell you more about how the Compton Effect is playing out today and being used today. So here's a picture of Compton about the time, about roughly, I think this is after his discovery. I'm not sure how long after, not much long after, I believe. I believe this is the 20s or so. And he, of course, was a professor here in the early 20s before going on to University of Chicago. We heard about him heading up the Manhattan Project, and then coming back here as chancellor and the things he did for the various departments here. We heard that in Lee's talk last week. So I'm going to bring it back to the science, though, this week. See if we... And remind you what the Compton Effect was. So really the great insight of the Compton Effect was that this was the experimental proof showing that light can behave as a particle. And so the concept is that a photon comes in, it has some energy to it, it scatters off an electron, and that scattering is just a pure particle scatter. Actually, I forgot something. Andrea, can I send you to my office? Very good. Send the postdocs to do. You will find a toy sitting on my desk that looked the supernova toy. It's not on the computer desk. It's probably underneath the FedEx box. The trash bin's still on the door. And if you need to get in, yes. My card apparently doesn't work. Yes. Someone gave her a card to get into my all right. Yes, I have one demonstration. Always have a demonstration. And of course, you're going to miss it online. But okay, back to the particle. So we treat light as a particle. And the idea is that because we can treat it as a particle, we can consider it as a scattering event, and momentum conservation and energy conservation is going to hold. So some amount of momentum goes from the photon, and energy goes from the photon to the electron starts moving, the light particle scatters out at an angle, and then just solving the energy balance and the momentum balance to conserve both, you can see that there's going to be a change in the energy or the wavelength of the scattered light, and that's going to depend upon angle. So a little bit of the energy is going to go from the photon into the light. And so this really was a demonstration that a photon is a real thing. These are the formulas, and we've discussed these in the past few weeks. The change in the light is going to depend upon the angle and some fundamental constants of nature. The speed of light, Planck's constant h, me is the mass of the electron, and that is the formula up there. So putting in some numbers to this, we can see that there is this quantity, h over MEC squared. We refer to that as the Compton wavelength. That is a fraction of an angstrom. Angstroms are basically the wavelengths of light that you expect for X-rays. And this is why Compton was working in the X-ray, because the characteristic numbers we're putting in here are in the X-ray regime. So that quantity there is called the Compton wavelength. Just to remind you, an angstrom is 1/10 billionth of a meter. Optical light is ranging from about 7,000 angstroms to about 3,500 angstroms, and that's the red to the blue. And X-ray light, for what I work with, tends to range from 1 angstrom to about 20 angstroms or so. So almost a factor of 10,000 times smaller wavelengths, and therefore 10,000 times higher energies. If you look at taking the formula instead of in wavelength shift and to look at the energy shift that Compton was looking at was 0.2 kiloelectron volts at an energy of 6.4 kiloelectron volts. And I'm going to tell you a little bit later in the talk why I've chosen 6.4 kiloelectron volts. It's a special energy that pops up a lot in astrophysics. But again, this change of 0.2 kiloelectron volts, that's the X-ray regime, and that's why Compton was working in the X-rays, because the characteristic numbers here he was looking at are relevant to X-rays. So the question is Compton scattering still relevant today? And yes, it turns out it's an extremely important process in astrophysics and cosmology. It turns out it's got a large role in creating or modifying the X-rays that we see coming from black holes and neutron stars. So it's an important process that we have to understand for that. It's an important process in creating emission from jets from black holes and neutron stars. Thank you very much. Yes, this is exactly what I was looking for. It also modifies the cosmic microwave background. The CMB spectrum, the cosmic microwave background spectrum, directly probes via the Compton effect the electron pressure in the early universe, and it's governed by something that we call the Compton Y parameter, and I'll explain that later. It modifies the cosmic microwave background spectrum as it passes through galaxy clusters, and that acts as a probe of physics and cosmology, and this is called the Sunyaev-Zeldovich effect. I'll also come to that later in my talk. So all these things will be explained in the talk today. So let's start off with the black holes and neutron stars. Black hole, sort of by the name, it's black. You don't actually see the black hole itself. It is what's left over after a star has used up all its nuclear fuel. Gravity collapses it. If that star is massive enough, if what's core is left over is massive enough, it collapses to the point that it becomes so small that it shrinks enough that light can't escape from the gravitational attraction into the black hole. It's shrouded in what's called an event horizon, and that's the region beyond which nothing can escape the gravitational pull of the object, not even light. So sort of by definition, you're not seeing the black hole directly. Neutron stars, slightly bigger than a black hole. There is a surface there. You can see surface emission from neutron stars. But for the most part, for black holes and neutron stars, we don't see them from the emission from themselves. We see the matter falling into them or onto them. And it's in the release of energy as the matter falls onto this object that we see these objects. And we're going to see that in the X-ray. So our naive expectation, and this is for a black hole, is that we're going to see these objects when they're in binary systems or in the centers of galaxies when there's a lot of mass around them that can fall into the gravitational attraction. And what we're going to see is the release of the gravitational potential energy as it falls into the black hole. So I have the black hole here in the center. It's going to have a characteristic size of the event horizon. The event horizon is scaled by the mass of the black hole, Newton's fundamental constant of gravity, g, the big G there, the speed of light, c. So putting in numbers to that, gm over c squared turns out to be a characteristic size scale. That is on the order of 1.5 kilometers per solar mass. So for one solar mass black hole, we expect the event horizon to be about a radius of 3 kilometers or so. 10 solar mass black hole, we expect 30 kilometers. And it turns out there's actually these gravitational, essentially the orbits are a little bit different in general relativity. So matter starts plunging into the black hole at a radius of 6 times this fundamental g over c squared. So at about 10 kilometers, matter falls in directly into the black hole. So if we imagine matter coming from a donor star orbiting around a black hole, it's donating matter to the black hole, but it has angular momentum, so it can't fall directly into the black hole. It's going to first form a disk of material around the black hole and fall through that disk. And as it falls through that disk, it's going to release gravitational potential energy. And all you have to do, basically, the expectation is that how much energy does it release as it falls to smaller radii towards the black hole? What is the area over which that energy is released. The more energy, the less area, the higher the temperature of the matter that's going to be falling in. So if you just plug in numbers to this, the expectations of what should be going on, you actually turns out have an awful lot of energy released. Plugging in those numbers for that gm over c squared, there you find out that you can release about 10% the rest mass energy of the material falling into the black hole. That's in comparison to nuclear burning, where you're releasing 0.7%. So it is 10 times more efficient than release of fusion energy. It actually could even be more than half the black hole spinning. The characteristic numbers here are, you expect, are about 1/10 of a kiloelectron volt to 1 kiloelectron volt. That's an equivalent temperature of about 1 million degrees to 10 million degrees, to put that in terms of temperature. So that's why we look in the X-ray. We would expect to see these in the X-ray. And the question is, when we look at black holes, do we actually see that happening? And the answer is yes, half the time. Here is one object in our galaxy, Cygnus X1, looked at in X-rays. It's actually looked at 2 times here. The spectrum on the left is what Cygnus X1 looks like half the time. The spectrum that's more to the right is the other half of the time. The x-axis there is the unit of energy of the X-rays. You can see it's running in a logarithmic scale from 1 kiloelectron volt, which is about 10 million degrees, to on the order of an MeV or so. So that's 10 billion degrees or so. And half the time we see a peak at this expected roughly 2 kiloelectron volts. So the peak of the peak where the spectra comes out for a black body is roughly 3 times the temperature. So in this case, the temperature is about 600 electron volts in this particular case. So an X-ray temperature, X-rays of the order that Compton was using in his experiments. However, the other half of the time for this particular object, we see instead the energy coming out at 100 kiloelectron volts. That's a much, much higher energy. Where is that coming from? And the answer is it's coming from Comptonization. So let's explain that. So the first naive expectation of how a black hole is going to work is how much gravitational energy is released per unit area. That would be black body radiation. You have some sort of thick surface of material in there. The energy is going as the inverse of the radius. The closer you get to the black hole, the more energy you release, and you're doing this over a smaller and smaller area. So the energy released is inversely proportional to the radius that you fall to, and the area is going as the radius squared. So it's going as 1 over radius cubed is basically what you expect for the energy release. And as you get closer to the black hole, that number is just going up and up and up, and that's why you expect X-rays. However, if we instead think of not of energy released per area, but energy released per particle, you can see that the energy per particle actually is a very large number. So let's imagine that particle being the electron falling into the black hole. And rather than that electron being in this nice, thick, geometrically thin, but optically thick disk, being in a big puffy cloud, which we call the Compton corona, if we imagine all these electrons falling in, what is the energy that they might achieve by falling into this gravitational potential? We call this the virial temperature. So just plugging in the characteristic radius for an electron falling into a potential of a black hole, you get the mass of the electron times the speed of light squared divided by that characteristic radius. Again, that characteristic radius in units of gravitational units is on the order of 10 or so. So you can get easily on the order of 10% of the rest mass energy of the electron into the energy of the electron. So its characteristic temperature, if it's not going through this thick disk, but is instead in this big puffy cloud, instead of being 1 kiloelectron volt, can be 50, 100 kiloelectron volts, a much larger energy. So in this case, we can have a situation where we might have a thick disk of material emitting photons at about 1 kiloelectron volt, being surrounded by this puffy cloud of electrons, which are at 100 kiloelectron volts. So unlike what Compton did, we have a situation not where the photon has more energy than the electron, and therefore the photon is giving up energy to the electron. We have electrons with more energy than the photons, and it's the electron that's going to be giving up the energy to the photons, and this is called inverse Comptonization. So this is a process that comes up all the time in astrophysics. So the idea is that we can look at the characteristic velocity of the electrons. It's going to have a thermal velocity. That velocity is going to go as the square root of the temperature. And that's in the frame of reference of us in the universe observing this effect. We can then just do the standard normal calculation that Compton did to understand his scattering by moving to the frame of reference where the electron is at rest. And Einstein told us with special relativity, we're going to see that the photons are going to get a characteristic boost in energy by what we call this gamma factor. This gamma factor is 1 over the square root of 1 minus the speed of the electron in terms of what fraction of the speed of light is the electron going to go at. And in that frame of reference where the electron is not moving, the photon does lose energy, but then we have to come back into the lab frame. And it turns out because the photon is going to be changing its angle, we essentially get 1 boosting factor for going into the electron frame, and we get a second boosting factor by coming out of the electron frame. So the characteristic energy transfer is going to be this factor of gamma squared, which is going to go as roughly the temperature of these electrons. So if you've got something on the order of the rest mass energy and temperature of the electrons, you can actually get a very efficient transfer of energy to the electron, from the electrons to the photons, which is why I had Andrea, you're not going to see this at home, but this is a little demonstration of the same concept done in, not unfortunately with electrons and photons, but done with bouncing balls. And rather than being able to change the energy of the system by changing velocities, we instead have a system where we have this part of the system, when I drop it, is going to have more energy because it has more mass. This is going to be our photon, a little ball here. This has less energy because it has less mass. We make freshmen do this calculation of how high this ball is going to go when we drop it. It's a classical problem that we assign for freshman mechanics, but it's the same concept that to understand how high this ball is going to go, you have to transfer them to the frame of reference when these two are what's called in the center of mass frame, where you're looking at the relative velocity between the two, the top ball and the bottom system being 0 in its rest frame, and then calculating momentum and energy transfer in that rest frame, and then coming back into the frame of reference that we observed from the laboratory. So I'm going to drop it, and someone can retrieve the ball later for me. Let's see how high we go. And you can see that, not for you online, but the small red ball went a really far distance, because something with a lot of energy transferring a little bit of its energy to something with not that much energy, it can gain an awful lot from that one scatter. And that's exactly what's happening here with inverse Compton effects, but it's the temperature of these electrons and the fact that the temperature of the electrons, thank you, is on the order of the rest mass energy of the electron itself. Each time it scatters, you're getting almost 100% change in the photon energy. Now that's by temperature. Similar concepts apply for purely kinetic effects as well, whether the electrons are moving because of temperature or whether the electrons are moving because of bulk motions in the material. So we're going to put a few formulas here, but don't worry too much about them. The basic concept is that hot electrons lose energy to photons, raise their energy. We can calculate that for a single scatter, and it's going to depend upon this gamma squared factor, which, as I said, is basically this velocity of the electron squared relative to the speed of light, which in this case is the temperature of the electrons relative to their rest mass. So you're getting these factors of order 100% per scatter. And then the question is, how many times does your photon scatter in this material? And that's going to go by the cross-section for the scattering, and that's called the Thomson cross-section, and what the density of those electrons are. And that's listed here. So we have this concept called optical depth, which is just the measure of the cross-section times the density integrated over the path that the photon takes. So the number of scatters is going to go as this optical depth parameter if it's less than 1, or it's going to go as the optical depth parameter squared if it's more than 1. So we define this thing called the Compton Y parameter, which measures the average change in the energy of the photons. And I put a subscript A there for this is the Compton Y parameter as defined by astrophysicists. We're going to come back to it later. Compton Y factor defined by cosmologists, slightly different. But for us in astrophysics, thinking about inverse Compton scattering, it's 4 times the temperature of the electrons relative to the rest mass energy of the electrons multiplied by the optical depth of the material that we're going through. But just to translate that into English, the more electrons the photons go through and the hotter those electrons are, the more energy the photons gain up until the point they get to the temperature of the electrons. This is described by what we call the Compton-Effect equation. Compton-Effect equation is a very complex equation. Jim Peebles, who won the 2019 Physics Nobel Prize, basically for literally writing the book on cosmology, that's really what he won for, is turning cosmological observations into real tests of cosmology, described the derivation of the Compton-Effect equation as a strengthening but lengthy exercise. So it's something that we make all of our graduate students do. So Nicole, have you done it yet? Have you gone and sat through, since you're working for Henrik, and we're going to see, has Henrik made you run through the Compton-Effect equation yet? Okay, so we know what she's doing on Monday. I spent a full day going through this, but we're just going to talk about the results of the Compton-Effect equation, not the actual equation itself. But the whole concept of the Compton-Effect equation is that we're applying what's called kinetic theory. We're not treating the photons as energy, we're treating the photons as particles. So we're looking at what is the number of photon particles per volume of physical space and per volume of energy space, their momentum. You know, what's their momentum in X, Y, and Z directions, and what's their density in X, Y, Z directions, and how many number of photons. We're treating the photons, again, not as a wave, but as actual discrete particles, and that's really what the Compton effect was all about. And because we're treating them as discrete particles, when doing the calculations, this is very amenable to what we call Monte Carlo computer simulations, where we follow the particles through a computer simulation where we look, does the particle scatter? Yes or no? If it's no, it comes into us and sees it directly. If it does scatter, we follow the particle a little further until next time it scatters. And we just basically follow the particles in the computer simulations as they go out. So this is going to be showing a little bit of a simulation of how inverse Compton scattering works. This is courtesy of a colleague of mine in Germany. Andrea in the audience, her former thesis advisor, did these computer calculations to show Comptonization. We're starting off with a situation where we have these low energy photons, all at a single energy. In this case, it is about 50 electron volts, I believe, if I'm reading that number correctly. I'm going to see how that spectrum changes for each scatter as these photons go through an electron cloud with a temperature of 200 keV, or roughly 40% of the rest mass energy of the electron. So after one scatter, you can see that most of them are being scattered up to higher energies on the order of 1 kiloelectron volt. After 2 scatters, it goes a little further. 3 scatters, further still, 4 scatters, 5 scatters, and we can keep going this on until we kind of like run out of statistics of the number of scatters not being important anymore, and we can add those up, and we get out a spectrum that looks like what we saw for the case of Cygnus X1, that we've transferred energy from the electrons to the photons. So rather than this expected 1 kiloelectron volt, we can get photons going all the way up to 100 keV or more. So we can apply this to observations of black holes in the universe, and this is applying that concept to real observations of that black hole, Cygnus X1. These are X-ray satellites that I've worked on for a number of years. Again, the spectra are ranging from roughly the equivalent of 10 million degrees to 10 billion degrees or so. And the y-axis is showing you the amount of X-rays at a given energy. And you can see that they're kind of peaking around the rest mass energy of the electron. So this component at the bottom here is the input low temperature photons coming from the disk, and they are at that expected roughly 1 keV. And then they are being Compton upscattered into this 100 keV spectrum. But there's a few more components that go into this. There's another component here, which as it turns out is also Comptonization going on in the system. And there's a couple of components here which are not Comptonization, but is part of the historical story of the Compton effect. We're going to explain all of this in a second. So we just talked about a process where we had a disk. That disk is emitting low energy photons. Those low energy photons go through a hot corona and get turned into high energy photons. But those high energy photons are going to come out of that corona and are going to come back and interact with the disk. So in this case, now we have hot photons interacting again with cold electrons in the disk. And so those hot photons are going to Compton downscatter and lose energy. And that's what that hump is that we were seeing there. However, this disk also has different elements in it. It's got carbon, nitrogen, oxygen, hydrogen, helium, and most importantly, it has a lot of iron in it, because these are systems that are very evolved stars. Very evolved stars at this point have made iron. At least one of the stars has gone supernova and turned into a black hole or a neutron star and created a lot of iron in that. And it turns out iron has a very large cross-section for interacting with X-rays. And so what we have happening here is that this is the iron in the accretion disk that is absorbing some of those X-rays, and it is kicking out an electron from the very innermost shell of that iron. That's the, in terms of quantum numbers, the n=1 shell, or else historically it was called the K shell when it was first discovered just by spectroscopy. Each shell of an atom, as far as its energy levels, had n=1, n=2, n=3, etc. But before they understood the concept of quantum numbers and quantum shells, they were labeled by spectroscopic line transitions, and it was the K, L, M, N shell. So you'll hear this either as referred to as a K absorption, a K edge absorption, or a quantum absorption from the innermost shell. Basically what we're doing is the iron is absorbing one of the photons and kicking out an electron from the very innermost part of the atom and kicking that electron all the way to infinity. And that happens at roughly 7 keV, 7 kiloelectron volts. But, however, on top of that, we then have electrons being grabbed by these bare iron nuclei at this point and going through cascading transitions. And the last transition is from the n=2 shell to the n=1 shell, or it's also from what we call the L shell to the K shell. And that emits a photon as that electron falls down in that potential of the atom, and that's called a fluorescence line. And that happens at 6.4 keV. And that's why I referred to, at the beginning of the talk, using that characteristic number of 6.4 keV. So we absorb electrons at 7 keV, and those, you absorb photons at 7 keV, and that's where we get that edge there in the spectrum, and then we fluoresce at 6.4 keV, and we get this line. However, that the story keeps going on here, that line itself is going to interact with the electrons in the disk and also go through Comptonization, and is also going to see this. And this is an example of a real observation of a neutron star. There you can see that edge of absorption at 7 keV from the cold material absorbing X-rays. We can see the fluorescence line at 6.4 keV of the electrons being recaptured by the iron. And then you can see a little bit of a tail at low energy, and that is Compton scattering going on of that fluorescence line, and we call that the Compton shoulder. And that ends up being a measure of the electron density and the density of the disk. It gives us some diagnostics of that cold material going on there. But an interesting historical side note is that Compton was actually the one who discovered the Compton shoulder. Now, fluorescence lines, because they're a quantum effect going from the 2 shell to the 1 shell, they happen at a fixed energy. So these fluorescence lines were known, but we didn't understand quantum mechanics at that point. So they were not really understood other than to notice that they were different than the experiment that Compton wanted to perform. He did not really understand these fluorescence lines, and he didn't want these fluorescence lines. So one of the genius, and this was talked about in Eric Henderson's thought, in measuring the Compton effect, was to create sources of monochromatic X-rays using scattering of X-rays off of crystals to get away from the fluorescence lines and to be able to control the wavelength of the incoming X-rays that were coming in. So that was talked about in Eric's talk about a month ago. However, it took him a while, about a year, to get there, to get from starting with systems where he was making X-rays with a lot of fluorescence lines in it to getting a monochromatic source of X-rays. So his first experiments were like October 1921. And if you go to the archives here and look at the notes, he notes that he's got this fluorescence line there, and that's a bit of a problem for his experiments. And there is this, he quotes it here, there is a bump in the general wavelength curve on the long wavelength side of the K lines. This is the Compton shoulder. And this is his data. It's a little hard to read. I'm not quite sure which is up and down on this, or exactly what the units are on this is, but this is how you recorded data back in 1921. This is from Compton's notebook. And you can sort of see there is the fluorescence line there. I believe that's peaking at roughly 6. I think this is a line of molybdenum. And then there is this little tail, so I believe the x-axis is wavelength there, and there's this secondary hump. That is him discovering Compton effect a year early, but as this little shoulder on the fluorescence lines, and he didn't quite understand that yet. But it is something that pops up in astrophysics all the time. Now, the story gets even more complicated because the black holes are more complicated than the simple picture that I showed you. We had a disk in there that gave us low energy photons, a corona in there that translated those low energy photons into high energy photons. We can also have a jet in there. So it turns out that when we see coronae in black holes, we also see jets. We see that via radio emission. And what we believe is happening is that the accretion disk is swirling around the black hole, twisting up a magnetic field which emerges from the disk, creates a funnel, and a jet of electrons and possibly positrons move along this magnetic field. And those electrons are going to spiral around the magnetic field. Electrons spiraling around the magnetic field creates what we call synchrotron radiation. That is going to be something that we see mostly in the radio and the infrared. However, that is low energy photons being created by hot energetic electrons, and they're in the same vicinity. So again, the story, it's a familiar story. What you create can then interact with you. So these low energy photons from synchrotron radiation can then themselves Compton upscatter off of the electrons that created them, and this leads to what we call synchrotron self-Compton. So we got a case where a disk makes low energy photons, Compton upscatters in a corona, a jet creates low energy photons, and Compton upscatters into high energy photons. So again, the same data, different model. We're doing a model where we put in this jet. It sees and it works as well. That we can have a disk, we can have synchrotron radiation from this jet, we can have Comptonized synchrotron radiation, and then we also have that interaction with this disk in the Compton backscatter. So again, this is ubiquitous in studies of black holes and neutron stars, and something that we really have to account for. Now, I said we see this in jets. Here is an optical image of an extragalactic jet. This is what we call a blazar. It is in the galaxy Markarian 421. This is an optical image. This galaxy is about 400 million light years away. We're looking at the center of this galaxy, and we're looking at the emission coming from that jet going on there. And here is a spectrum of that emission over many, many, many different wavelengths. So again, the x-axis is energy of the photons. The y-axis is sort of an integrated account of how much energy there is at each different wavelength. And these astrophysical jets around supermassive black holes span an enormous range of energies. They go all the way from the radio to the optical, the X-ray, the gamma ray. They even go beyond the gamma ray to what we call GeV photons and TeV photons, a billion times and a trillion times an electron volt. So orders of magnitude higher in energy than we've been talking about so far. And in this case, the concept, at least one of the concepts for explaining this, is that first hump that you see there is synchrotron emission from particles spiraling around this jet, and then that second hump that you see there is the Compton scattering of those low energy photons in the particles of the jet. So applying that model to the data, and this is a lot of different satellites and ground-based observatories working together, that hump there is the synchrotron radiation, and then that hump is possibly synchrotron self-Compton going on. So I've actually taken these pictures from some papers, and actually the first image was from the Wikipedia page. And one of three references on the Wikipedia page is from Andrea. So if you have any questions, Andrea will happily answer them at the end of the talk instead of me. Yes, I'll put you on the spot, Andrea. Just to put some numbers to this, the speeds that we're getting out of here are very, very close to the speed of light. Again, we're using this relativistic gamma factor, which is 1 over the square root of 1 minus the velocity squared. The closer you are to the speed of light, the larger the gamma is. Gamma of 20 to 50 is huge. The energy in these jets, in the magnetic field, in the electrons, and in the photons themselves, or those are the three different numbers there, are on the order of about 10 billion times the amount of energy being put out by our sun. And the synchrotron self-Compton story gives a consistent story for variability that we see in the system. That if we look at the system with different satellites at the same time, we see the X-rays go up, and at the same time, we see these TeV electrons go up at the same time, despite the fact that they are 1 million times apart in their energies. And this is an example of that you see the X-rays flaring up here, and at the same time, 1 million times higher in energy, you see the flare in the TeV. So the idea being that the X-rays are coming partly from the synchrotron radiation, and then the TeV is coming from the Comptonization. And this is all happening very, very close to the black hole, and that's why the timescales can be so commensurate with each other. And so happening in a radius of about 50 times the radius of the event horizon of the black hole. Now let's turn to cosmology. and talk about Comptonization and cosmology for the end of this talk here. Here is the microwave spectrum of the cosmic microwave background. This is in essentially the radio, very long wavelength radio. This is done in terms of essentially the x-axis is frequency or inverse wavelength. The peak is at about 1 millimeter waves. The temperature, the equivalent temperature of the cosmic microwave background is about 3 degrees Kelvin. It's very close to absolute zero, and that's why we see this. This is the residual heat of the Big Bang that is everywhere, somewhat isotropic on the sky. And this won a Nobel Prize in actually several times. First was Penzias and Wilson for discovering that this was in the background. And then John Mather and George Smoot won it in 2006 for characterizing it, the spectrum very well. This is a near perfect black body spectrum of 3 degrees. However, this black body spectrum could have potentially been altered by Comptonization in the early universe. Because it's such a low energy, and we would expect any electrons in the early universe to be hot, we'd expect that the electrons to give their energy to the photons rather than what Compton saw with the photons giving their energy to the electrons. So what would happen is that the low energy photons from the cosmic microwave background would lose energy, and the high energy photons would gain a little bit of energy, and you would distort the spectrum from the cosmic microwave background. And you can characterize this by, again, this Compton Y parameter. It's going to be slightly different than we did it before, but one of the things they did with COBE, the satellite that did these measurements in the 90s, was to say that this spectrum is very, very, very close to a perfect black body, and the distortions on this perfect black body as characterized by this Compton Y parameter is almost on the order of only 20 parts in a million or so. So that the Compton Y parameter is less than 2 times 10 to the minus 5, which basically is saying it's a very near perfect black body, and that was part of the Nobel Prize. So that says that the early universe, after the cosmic microwave background was formed, did not have a lot of hot electrons, and it gives us a limit on what the universe looked like right after the cosmic microwave background was formed. The other thing that COBE and subsequent missions did was look at distortions of this microwave background. And those distortions are due to fluctuations in the early universe. Those fluctuations are different temperatures in the just small deviations about this mean temperature of the microwave background. Those look exactly like black bodies. They don't look like Comptonization. They just look like black bodies with slightly altered temperatures, a little lower in some places, a little higher in some places. And those temperature changes that we expect, again, are going to be on the order of 1 part in 100,000 in terms of the distortions, or so in terms of temperature. Comptonization, on the other hand, alters the shape of the black body spectrum. So Comptonization is going to look different than these alterations of the microwave background. One's going to look like just distortions of temperature. The other's going to look like distortions of spectrum. So here is distortion of temperature map done with a satellite called WMAP, the Wilkinson Microwave Anisotropy Probe. And that's after 9 years of studying the cosmic microwave background. They were able to measure distortions on the order of 1 part in 100,000 or so. And they measure this on a number of different angular size scales. However, we can use the Comptonization. And this is how the cosmologists define the Compton Y parameter. Again, it is basically the electron temperature integrated over the electron density multiplied by what's called the Compton cross section, or basically we're measuring the pressure of the electrons. And if you just look at sort of this tail on low energy photons, it's going to look like changing. If you just look at the tail, you can characterize that by a temperature change, even though you are really changing the whole spectrum. And putting in numbers to that on that, what we call the Raleigh Jeans portion of that black body tail, you can get something that is 2 times this Compton Y parameter, distortion in temperature. We're going to put some numbers to that in a second. Where would you likely see this alteration in temperature due to hot electrons? Well, one great place to look turns out to be clusters of galaxies, and this is called the Sunyaev-Zeldovich effect. So the idea is, here's a picture taken with the James Webb Space Telescope, as well as the Chandra X-ray Observatory. So the James Webb portion of this picture is in the infrared. It is essentially all those red streaks you see there are galaxies. And you can see that there's this just central concentration of red galaxies. That is a cluster of red galaxies. All these galaxies are gravitationally combined. They are gravitationally interacting. They are a gravitational unit, essentially. They are bound together by gravity. In between these galaxies is hot gas. That hot gas is going to emit in the X-rays. So we see the galaxies themselves in the infrared. We see the gas between the galaxies in the X-rays. That's called the galaxy cluster. That hot gas making those X-rays is at a temperature higher than the microwave background photons. So they are going to Compton upscatter the microwave background photons. And if you put some numbers into that, the gas from those galaxies is about 4 kiloelectron volts. The density is about 3 times 10 to the minus 3, 1/300th of a particle per cubic centimeter. The radius of that, you see there, is about 200 kiloparsecs or so. Plugging in those numbers to the Compton Y parameter, you would get this equivalent temperature change of about 5 times 10 to the minus 5. That's bigger than the distortions from just the fluctuations in the microwave background that you naturally expect. But it's going to be localized to wherever there are galaxy clusters. So this turns out to be, it is a tricky measurement, but it is a doable measurement, and it's a way of discovering where these galaxy clusters are. And this is being done with the South Pole Telescope via a Sunyaev-Zeldovich survey. I'm going to show you data from that. So here is microwave observations at 95 gigahertz of the microwave background. You can see some point sources in there. Mostly what you see is just the fluctuations in the microwave background. You could also do another observation at 150 gigahertz, and we can kind of go back and forth between that. And if you look carefully, you might see one spot which is pretty consistent in both. You can get rid of the point sources, but there's one dark spot which is in both of these images. And so what they essentially do is they both filter on the size of the fluctuations and the temperature change of the fluctuations, and filter out the cosmic microwave background part. And what you're left with is this kind of glaring hole in the image, and that's a galaxy cluster. So this actually becomes a very good way of discovering galaxy clusters. Now, the Sunyaev-Zeldovich effect is basically a measurement of the pressure of the galaxy cluster. It's a measurement of the temperature times the density. The X-ray emission comes from what we call bremsstrahlung emission. Bremsstrahlung emission is a product of the density squared and the square root of the temperature. So if you can measure both the X-ray emission and the Sunyaev-Zeldovich effect, you get these nice constraints on both the density and the temperature in the system, and it allows you to start measuring the properties of the galaxy emission going on. You know the electron density, you know the electron temperature. Now, all the emission and Comptonization comes from the electrons. Electrons are leptons. These leptons are in balance with the baryons, the protons and neutrons that make up you and me. But as we know from cosmology, most of the matter in the universe is actually dark matter. The dark matter is what's driving the gravity in these galaxy clusters. We can measure that gravity by essentially measure of the pressure. These clusters are in hydrostatic equilibrium. Gravity is kind of pulling it in and creating this pressure that we can measure in the electrons. We can also measure the dark matter, going back a few slides. You can see that all those red galaxies there look like they're kind of encircling the cluster. You might see there's some distortion to the shapes, that they all look like they're rotating around the center. That is gravitational lensing going on, distorting the shape of the galaxy. That gravitational lensing also gives us a measure of the mass in the dark matter in the cluster. So we have, using Comptonization and the Sunyaev-Zeldovich effect, we have a lot of nice measurements when combining with other things. We can measure the dark matter, we can measure the baryon matter, and then we can compare these to cosmological models and derive inferences about the density of the universe. And that's what's going on in here in this figure here. You might have heard about the fact that the universe has a lot of different components to it. It has baryons, it has dark matter, it has dark energy, and we can characterize this in a normalized way. If the universe is at what's called the critical density, where we expect it to be uniformly, to be expanding in a flat geometric state, the total density of the universe should be 1 in this normalized way. And 1 when we take dark matter, baryons, dark energy, and add them all up together. And right now we're in a universe that is dominated by this dark energy. That is that omega lambda on the side, the y-axis. And the other major part of the universe is dark matter. Us, the baryons, aren't even listed on this plot because we're only 5% of the universe or so, and that's the other 95% of the universe. There are different measurements. A Nobel Prize was given out in the early 2000s for measurements of supernovae, which gave a constraint for the dark energy. That's the green curves. The cosmic microwave background we already discussed was 2006 Nobel Prize. That gives a constraint on the total amount of these different pieces added together. That is the curve that you see in the blue, kind of going diagonally left-right. And then these cluster measurements is this vertical curve here. And that's a combination of Sunyaev-Zeldovich effect and Comptonization going on at the same time. And putting all three of those together, you start getting very accurate models of the different constituents of the universe. So I'm going to end off with Wistful physics today and the Compton effect. We'll kind of go through this really quickly. Do we work with Compton effects still in the Wistful physics department? The answer is yes. So Wistful physics in the McDonald Center, we have a very cohesive group of astrophysics and cosmology researchers. Our main focus here in the department is high energy astrophysics and cosmology. We have about 10 tenure track faculty in these areas. So the Compton effect really is our bread and butter as part of the things that we do. And both from the point of view of experiment, observation, theory, and statistical analysis. So I'm just going to go through some highlights of what we're doing today after one more historical side trip. The first historical side trip is to Eugene Feinberg and Henry Primakoff, who published this paper in 1948, Interaction of Cosmic Ray Primaries with Sunlight and Starlight. This really is like the first astrophysical application of the Compton effect. They concluded that cosmic ray electrons could not be extragalactic because they would inverse Compton scatter off of starlight in the universe. So they couldn't have traveled between galaxies. It'd be too far to go without losing energy. So they have to be the electron part of the cosmic rays, at least, had to be much more local. So this was really one of the very first astrophysical applications of Compton scattering. But today we've got a lot more going on. Jim Buckley is working on an experiment to measure the MEV spectra using the Compton effect. I should have pointed this out going back very quickly to the spectrum here. you'll notice that there's this gap between these two peaks. And then you might think that this is where all the interesting stuff is happening. There's this gap because that's around an MeV. That is roughly the energy of the electron. It is really, really, really hard to create a detector that measures something when the material of your detector has that characteristic energy. So the rest mass energy of the electron is happening in that gap, makes the measurements very tricky to perform there. But Jim is working on a detector that is using the Compton effect to advantage to detect these MeV photons. So basically the idea is that a photon comes in, interacts with the detector, Compton scatters an electron, and then keeps going. And Compton scatters again off of more electrons. And basically you're using your knowledge of the Compton effect to figure out what direction this photon came from on the sky and what the energy of that photon is. So basically you're just adding up the energies that you detect in your detector to figure out the angle, your initial angle and initial energy of the MeV photon that came in. So basically it's using the Compton effect to create the detector, and that should hopefully fill in that gap you saw in the jet spectrum. Manel Arando is also working on similar concepts. So he works with both satellites in the sky and ground-based TeV detectors specifically to look at these kind of jet sources where you see the synchrotron radiation being Compton upscattered into these powerful TeV photons. Henryk Kaczynski, he was in the record the other day, was doing models of corona. The other new twist, and this was discussed in the record, is that Comptonization is not only something that happens as a function of energy, it happens as a function of polarization of the X-rays. What is the direction of the electric fields and magnetic fields in these photons? And there is actually a polarized component to the scattering cross-section. So being able to measure energy and polarization at the same time gives you a good idea about the geometry of these systems. And this is a very recent set of observations where the middle is an image of the radio jet in Cygnus X1, the black hole I showed you earlier. And at the side there is the direction of the polarization measured in the X-rays very recently, and you see that the X-rays are very well aligned with the radio jet, and that's going to help us with models. My own work, there we go, deals with trying to put together variability in the X-rays with the spectral models of these corona. And what you actually see is, and there's an image of the X-ray variability on the side, these X-rays are kind of going up and down on time scales ranging from 1/10 of a second to 100 seconds, where we're basically turning on and off 100,000 suns over these second time scales, and we're seeing spectral changes at the same time. So I try to understand the geometry by coupling these Compton models together with the variability. Professor Yajie Yuan, recent hire here, does numerical simulations of these Compton coronae. We don't really understand yet the mechanism by which the energy gets into the electrons in these hot coronae. So that's one of the things that Yajie is working on. She's working on models of accretion disks twisting up magnetic fields, which you're seeing that here. Those magnetic fields reconnect and release energy, and that energy goes into the electron. So she's trying to numerically simulate the processes by which the energy moves from the accretion disk into that hot corona. And that's something that she's trying to understand. Alex Chen, working also on numerical simulations, is working on cases of pulsars. And pulsars are kind of like this black hole situation. These are neutron stars. They create synchrotron radiation that is creating the low energy photons, which then is going to be upscattered in the electrons in these spinning neutron stars with intense magnetic fields. Professor Joanna Nagy is working on the Sunyaev-Zeldovich effect. In fact, Joanna right now is actually at the South Pole putting together detectors to do surveys of Sunyaev-Zeldovich effect, identifying galaxy clusters to do cosmology. And Professor Andrina Nicola is someone who works with these big data sets to translate the results of these experiments into cosmological constraints like I showed you. So the Compton effect is something that we really do use every day here at Washington University. But to sort of like take a step back here, like many ideas in physics, the Compton effect started off as an experimental demonstration of a theoretical idea. Actually, I really think the experiment came first in a theoretical notion and said, it's that. He was really doing more purely for the point of view just to find out what happened. But like a lot of things in physics, you start off demonstrating something in the lab, but then as you demonstrate it in the lab, you turn around and find out that it really happens in nature as well. So if we have cases that create spectra of compact objects, it creates the emission from jets. It modifies the cosmic microwave background. The next step often in physics is after you see it happening, not just in the lab, but nature in general, is that you turn around and say, how can we use this for purposes that we didn't think about? So it started off here at Washington University using the Compton effect to rule out extragalactic electrons, using the Compton effect to identify galaxy clusters and then constrain cosmology. Nothing to do with the Compton effect, seemingly, but very important for understanding cosmology. And then turning around and using it in detectors. Now, I think the interesting thing about this is where we're probably going with a lot of different things. Modern quantum detectors really take advantage of the fact that the Compton effect is talking about individual photons. New modern detectors in astrophysics really are measuring the properties, whether it's in the infrared or the X-ray. We're measuring a single photon at a time. And we're doing it with pretty good fidelity, almost getting 100% of all the photons that come in. So kind of looking forward to the next 100 years of Washington University physics, we've got folks right now working on quantum entanglement. Eric Henriksen is working on macroscopic quantum effects in materials. So it'd be interesting to come back 100 years from now to see what the lab work we're doing here in quantum now translates into the future of detectors of what we're going to be doing 100 years from now. And I'll end the talk there. So any questions from the audience? Lee.
So, Mike, going back to the first case of matter and falling into the black hole and the electrons, the Compton scattering, upscattering the photon in some spherical shell and thinking about that. And then the way you treated it didn't have the angular dependence. But the electrons are, the gamma is this large number, but it's radial, it's inward. So those photons are upscattered towards, mostly, towards RE0, aren't they?
Okay, so we just...
There must be some thermalization that allows it to come back.
Yeah, so we essentially asked the question about the geometry of Compton coronae that I showed for doing these models. And the question is that does the scattering preferentially scatter things towards the center? The answer is that it gets complicated, that you actually, when do this properly, you have to put in the general relativity so the photons actually orbit around the black hole. Also, the corona actually is, we're trying to figure out the geometry, and the geometry does make a difference. The corona could be moving. If the corona is moving, if the corona is really like the base of the jet, it's moving away from the black hole. And if it's moving away from the black hole and close to the speed of light, it's going to beam the radiation away from the black hole by its bulk motion. Also, the fact that there's an edge to the corona. It's
compared to the electron's gain of energy
Yeah, but it can beam. It could be small in terms of the gain of energy could be small due to the motion, but the beaming is, you only need this gamma of roughly 2 to get a little bit of beaming away. So these issues do go in there. You actually do follow the geometry, and there was some thought with very, very early models that you see asymmetries in the spectrum as a function of angle, but those were very highly idealized geometries. Usually, because you're looking, all the X-rays that you're seeing are multiple scatters. So after the first scatter, they've essentially lost knowledge of where they came from, and so they tend to be fairly isotropic after the first scatter, and they do then end up coming out the side where there is no electrons. So yeah, it's a great question, but it's one of those things where you naively do it, you don't think about it, then you go a little bit more sophisticated and you worry about it, and then you go a lot more sophisticated and you say, okay, it's not a problem. So we're up to like the step 3 part, and now we're adding more back to there's more problems that we haven't thought about. So it's those 2 steps forward, 1 step back kind of thing as far as the complications that get put into these models. And we're at the level that we're doing things like putting in the relativity and things like that to account for the fact that gravity distorts the direction at which these things come out, velocities distort the directions that these things are, and we have to worry about that. Back there.
There's 2 words that you've used this morning that I know. One is microwave and the other is X-ray.
Yeah.
So all of your discussion this morning to me is truly educational, but only in a very small way because way far beyond my understanding of the research that you do. But I came last week and this morning because I was very interested in knowing how Compton and what he's given clearly to the world in terms of physics. So if you would be so kind, because I have a microwave and I've had lots of X-rays, what would you say to the ordinary person who has a very standard brain, if you will? What does this mean both to, let's just say, to our country, to the world, where we are today, with so much occurring that could say, at some point in time, the Earth is not going to exist anymore. So if you could just give me some sense of what your research would be representing to the ordinary person.
Okay, the bottom line is, what does my research represent to the ordinary person? This is always a difficult because we're not curing cancer, needless to say. However, but I think one of the points is that anytime you have basic physics research, and again, and that's why I was trying to come back in the end here, Compton was just doing these experiments for basic research. Just what does an X-ray do when it scatters off an electron, and what does that demonstrate? And for him, it was just demonstrating that, hey, light's a photon. It's a particle. It acts like a particle. He had no concept of where that was going to go beyond that. And again, every time we do something in physics, it usually ends up that, okay, we can demonstrate something in the lab, but then you turn around and we tend to find it actually occurs in nature, not just under controlled situations. So the difference between astrophysics and laboratory physics is that I can't control my experiment. I can make something up that is perfectly consistent with the laws of physics, but if nature doesn't do it, I can't study it. Turns out nature tends to do an awful lot when you look hard enough. And then the next step that we tend to go after, okay, can we demonstrate it in a lab? Yes. Does nature do it? Surprisingly, yes. We then turn around and say, can we harness it? And sometimes, the way we start harnessing it is we go back and do the things that kind of interest us as physicists, like cosmology. We are harnessing Compton Effect to study cosmology, but then we turn around and make much more practical detectors that then get used in things like MRI and CAT scans and other things that surprisingly end up being useful. I'll give you one other example, and I'll let Lee mention in a second. One of the things that blew my mind is that when I was in grad school, I heard a talk about timing of pulsars and how accurately you had to run a clock to time a pulsar, just to calculate. And when I was in grad school, a pulsar was the most accurate clock we knew about, and it took the best clocks in the world to do those timings. I was then on a diving trip 20 years later, talking to a guy working for a cell phone company, and it turns out, I found out from him, the clocks that we were using to time pulsars are now routine in cell phone towers. And the fact that we can use cell phone towers is because we have clocks good enough to have studied general relativity. So it all kind of gets together. You never know where the things go in the end. You kind of follow the curiosity, and they end up being practical even when you didn't expect them to be. Lee, did you want to add to that?
Close the circle. So there's two guys sitting over there. They click away. You're WashU's expert on positron emission. Okay, they have a background in their work, which is Compton Scattering, sort of a new. Okay, and so they're experts in it because they want to get rid of it. But they also have an interaction with one of the people that Mike talked about, Jim Buckley. So there's a technology overlap between this cosmological research and what goes on in that. And so, the camera that the Jim was showing to the spectrum, we call it a Compton Effect. Right. So they use technology in med school that is being used for these space sciences, and the people know each other. Okay, they talk to each other from the med school, and so that goes on.
Yeah. So Lee, for those online who didn't hear that, Lee basically pointed out that Jim Buckley here in the department is using similar essentially the same technology to study extragalactic jets in collaboration with folks at the medical school to study these things much closer to home. All right, so in the back there, we got a question. The question is about, is the background radiation related to the multiverse? The best explanations we have of that is that really it's just quantum fluctuations in our own single universe that have been blown up to large scale. And so it doesn't really have to be a multiverse. The only really strange thing about our universe is that for the largest scales, the amount of fluctuations on the largest scales is a little bit unusual. It's not exactly what you'd expect for just a random draw of the dice. We're a little bit, I think we're a little bit overpowered at the largest scales. Just slightly weird, but it's the question is are we one of many universes, and we're just a little bit off the average, and not so far off that life couldn't form, but far off enough that it's a little slightly unexpected. There's lots of people who are trying to figure out whether there is any testable evidence to say that we're one of many universes. I think the closest I've seen is not those little tiny fluctuations, but the biggest fluctuation were slightly unusual in that case. Although I have seen other cosmologists. There's one famous one, Rocky Colbert, University of Chicago, who says that any talk about the multiverse and anthropic principle is a disease that should not be tolerated within cosmology. Maybe not an exact quote, but yeah.
How has the Compton Effect contributed
Oh, well, the Compton effect is I say it's huge in modeling the spectra of black holes. So it really does give us, with the models that we have, a very good idea that these things are very compact. The size scales of these, that they really, everything is happening within just a few times the event horizon size. So the models that we do based upon the spectra and the variability that we see when modeling the quantization, these things can't be more than about 100 times the event horizon. So you are literally seeing, for the galactic ones, 100,000 suns turning on and off in a timescale of a second. And based upon the Compton measurements, knowing that that is all happening within 50 times the event horizon. So it really is giving us a very good idea of the size scale and something about the geometry going on these systems. It'd be really impossible. The spectral models I've shown you would be impossible without putting in the Compton effect. And then for things, like I said, the Compton shoulder on that fluorescence line of iron is giving us very good knowledge about what the density and, to some extent, the geometry of that material is. These things are too, with the exception of the Event Horizon Telescope, which we've imaged 2 black holes out of the many black holes, these things are far too small to ever get an image of. So we have to infer their geometry and size from secondary concerns by basically doing these models of spectra and variability and polarization to kind of back out what's going on there. And understanding the Compton effect is really important for that. Yeah.
Saying that the Cygnus X1 has 2 different spectra. How did you? Maybe I missed it. How often are they switching back and forth? Why do you think it's happening?
We don't know why. The answer, so for those online, the question is, why does the spectrum of Cygnus X1 go back and forth? And the answer is we don't know why it goes back and forth between this thermal state and this Comptonization state. It can happen over the time scale of hours. It could go from one to the other. After it does happen, it can stay there for weeks. It sometimes can just like fake it, like it can almost go there, and it looks like it's going to go there, and then it doesn't go there, and it can happen, and that can happen over the time scale of hours. So the transition from this disk to this Compton corona can happen literally in hours, and when it happens, it could stay there for weeks, and it's roughly 50-50 over the past 30 years that it's in one of the. Again, these things, physically, it's about 50 times, 100 times the event horizon. So the event horizon in Cygnus X1 is about 60 kilometers. So this is about 6,000. So it's about the size of the United States. So we have this whole transition where we're altering the character of something that is emitting 100,000 times the sun in the size of the United States, transiting its character in a quarter of a day. And it's turning on and off 10 to 40% of its energy on a second time scale. So it's going 100,000 suns up and down 1 second time scales.
Right, with more energy being shifted to a higher frequency.
Yeah.
That's when it's emitting more energy.
Yes. Well, actually, it's almost the same. It's really Cygnus X1. It's fluctuation about a mean, and so in whether it's a disk or a Compton corona, the energy, at least in Cygnus X1, is about the same. Most other black holes, when they are bright, look like a nice, well-behaved disk, and when they are fainter, look like a Compton corona. We don't understand exactly what that transition is. It is absolutely related to when they feed, and it is absolutely related to how they feed, and that would be a whole other talk to go through. Yeah, Lee, you had a.
Well, that was the question. Is it feeding? Is it in a binary?
Yes, these things have to be in binaries to see. The question was it in binaries? Now there's some questions online. Can I actually get to see what those are? Show me. Can you address PET scanners and Michael Prigozhin? Can anyone here address PET? Turbogosian. No, I personally cannot. Yeah. So.
Well, we said Prigozhin, early in the 70s, so they, I mean, fusion tomography imaging was, and positron imaging, this was there was some of the people working on it, but probably inspired by the work on cell decided to build a ring test scanner in the current geometry, and hired two graduates from UCLA, Michael Phelps and I can only graduates of I think we're postdocs on Mike Phelps other that was in the early 70s, and I said inspired probably from the work on cell scanners on so the tomography images and the ring test scanners, and so we start from there. So open up and went to Oak Ridge, worked with physical engineers working at ECMG or Tech to help out with electronics, and that's good at spin off as a full test scanner, commercial test scanners. We're quite successful. So now the historical line. In my talk, I mentioned some of the people that Compton hired. In the next generation of people hired, they educated the people who made PET, positron emission tomography. So Washington University does have a strong claim on inventing positron emission tomography, and you can make a direct scientific genetic line that
Okay, so for those online, basically Lee and others are pointing out that there is always this line from fundamental research in physics to that ends up being practical. It's a game we kind of play with the different fields of the sciences. Mathematicians try to invent math that's useless to physicists. It always fails. Then physicists try to do things that are useless to engineers. It always fails. So it's hard to come up with something that someone clever won't find a practical use for one way or another. So it's the great circle of life, from math to physics to engineering and onward. Yeah.
Mike, I hope you don't mind if I make a comment instead of asking a question.
Okay, we'll get a comment instead of a question. Go for it.
I think we all owe the physics department for a marvelous, dedicated series to somebody who has been amply pointed out, did both science, the world, through the Manhattan Project, and Washington University as scientist and chancellor. But for me, to quote Yogi Berra, this was like deja vu all over again. Because in 1950, I sat in the third row there and took a physics course. I was a senior at the time, took a physics course from Henry Gromyko called Modern Physics. And one of the topics discussed was Compton Scattering, in addition to many others. And Henry at the time was being wooed by other universities, wined and dined, and he had to be away during one of the weeks of the course for 2 periods. Those periods were covered by Arthur Compton. So I sat in this very room listening to him, standing where you were. And he chose, instead of continuing the coursework, to give 2 days, a 2 days little mini course on the history of physics, including some readings in the library in a book called Dampier, written by Dampier, so that we would learn about a little bit about the history of the subject matter.
All right, so we have someone here who is just giving us a story about having sat in on a lecture by Arthur Compton when he was a senior here at Washington University, listening to Compton talk about physics and modern physics back in the 1950s. So yeah, so at some point, this is always a fun thing with physics, is kind of getting to hear some of these historical talks and the people who actually did the work. For another time, when I'm not being recorded, I will happily give anyone here my whole list of encounters with Nobel Prize winning physicists over the year, which I can see Audrey shaking her head. Yes, I will not record those stories for posterity. Although maybe just to briefly mention the time that Nobel Prize winner Bob Laughlin explained the concept of mortality and death to me. But a story for another day. These things are fun. Washington University does have a great history of interesting things having gone in the physics department. So it's one of the things we wanted to highlight with this talk, but other things we wanted to emphasize is that hopefully the history is not over. that this is just, from Compton and Primakov in the 40s. And as I said, I don't know exactly what we'll be talking about 100 years from now, but I do have faith that some of the really interesting things that's happening in the labs downstairs, and Johanna at the South Pole right now, Jim luckily will be going to the South Pole, and all over the world, that there will be some interesting stories to tell 50 years from now or 100 years from now, based upon some of the stuff we're doing today. So maybe with that, I will end off things, and thank you for all coming, and we'll start it up again next semester in the spring.
Thank you.
And thanks for being online.